Hello, good evening all. So my name is Parth Joshi and I am a PhD student at IIT Bombay and as a part of the Prime Minister's Research Fellowship program. So I am here to conduct some of these weekly problem solving sessions for you and yeah, so this is the problem solving session for week 5. Yeah, hello, good evening Amit sir and others. So good evening all. So, like because of some medical emergency at my home, I actually had to postpone this session to Tuesday. So, yeah. So yeah, so I have been conducting these weekly problem solving sessions, and so we have been discussing the some problems related to the content for that week, and yeah, so we also like tried to address some of the doubts that you may have related to the course content for that week. So yeah, so that's the general agenda. So yeah, so before we begin, so just wanted to know like anyone has any questions or comments to share. So anyone has any questions or comments or any doubts related to the content for week 5? Yeah, good evening, Mr. Prashant. So am I clearly audible? So am I audible? Okay. Yeah. Okay. So like basically what I had planned for today is like I wanted to show you one demo like before we begin with the okay, so you have a question related to will there be numericals on variable resistance transducer or electrodynamic transducer? Uh, I am not sure. Like, I mean, like, can you just point me to the? So, Mr. Prashant, so can you please point me to the particular section of that, like, to which you are referring to? I mean, so if you could just like even like if you can share your screen or something like what exactly I didn't get your question. Yeah, four type of transducers. Okay. So I'm not sure like about your like particular question as such because uh, but so can you just
One
tell
minute,
me
sir.
what? So if you can just
1 minute,
unmute
sir.
and tell me what exactly is like which is the question or like which
Yes,
section are
sir.
you
Yes, sir.
referring to for the yeah
Am I audible, sir?
yeah yes
Hello.
hi hello Mr.
Sir.
Prashant.
Because sir taught us four types of transducers. That is the
Okay,
variable
yeah,
resistance transducer, piezoelectric transducer,
right,
then electrodynamic transducer,
right,
then hello, uh, LVDT, linear variable.
right. Okay.
सोमला कॉल करू नको.
So it's
Hello,
like you're
1 minute.
basically talking about
LVDT.
the lecture 21 like that the
Yes.
first lecture for this week's content, right?
Call is disturbing.
Yeah, so I think there like so for any transducer as
Hello,
such,
hello,
there is like one simple basic physical principle on which they are based, and so you can expect some simple numericals on that, like where so like so you have
hello.
these variable resistance transducers, so where uh, so you will be given some, it's
Uh,
a basically a Wheatstone's bridge circuit, right? So which
yes, yes, yes. So, sir taught the relation between the strain, means strain in the strain and voltage output.
right,
So, some relations, formulas related to that.
right,
And so taught to then electrodynamic transducer, that is output voltage related to velocity, how it is related.
right,
So,
right, right.
but assignment there is no question related to this.
Yeah, so in
And
the assignment, it may not be there, but it's like, so you can just kind of try to understand like the basic physical
yes, sir.
principle. So it's basically, so transducer, the basic principle, I hope you understand, like that, so it's like some, uh, it's basically conversion into an equivalent electrical signal. So let us say if some motion or some physical, like some force or pressure or displacement or something, it is converted into an equivalent electrical signal. So in case of this strain gauges, so you have some, so the deformation is like basically being because of the uh, this variable resistance or piezoresistive, what you can say, this transducer, so that can be you can get an equivalent electrical signal for that. Similarly, for piezoelectric transducers, so you get an equivalent electrical signal proportional to the force or load what is applied. So you can just note the basic principle as such, and so there may not be like very detailed problems on that, but just maybe some simple numericals might be there, where you might be just asked to find out what is the, let us say, proportional electrical signal uh, for a given certain whatever like in this case of this electrodynamic transducer, so you have basically the up and down movement, so that like the velocity of that, let us say, coil, like moving up and down, so through the magnetic field, and so there is a voltage generated which is proportional to the magnetic flux density, the length, and the velocity of that coil. So you can basically just try to understand the basic physical principle, and like there might be very simple numericals as such, or I think
Right, right.
so.
Mostly the numerical sound around vibrometer and the accelerometer,
Yes.
sismometer, right.
Yeah, so the I think most of the content, rather assignment content, is focused towards that. Um,
Right, right.
but yeah,
Okay, sir.
so like in terms of like the frequency response over a large range of frequencies, how does the measured the measured quantity versus the input whatever like that, so that is like the frequency response curve that you have studied. So that I think is mostly discussed for this vibrometer or seismometer or accelerometer, that kind of devices, right?
All right, sir. Okay.
Yeah. Any other questions?
No, sir. No, not from my side.
You are finding some difficulty in solving some questions in the assignment. So would you take a few sample problems today? Yes, I will be taking some sample problems today. So hopefully those would help you in solving those problems. So if the problems don't answer your questions. So do let me know. You can bring up that during the session. So we can try to answer that. Right. Yeah. So what I had planned like a short demo of. I also wanted to show you like a small demo on MATLAB, not related to the specific content for this week, but like generally how you can use MATLAB as a tool to solve some simple vibration problems. So that's I wanted to just demonstrate. So are all of you interested in going through that? Okay. Okay, Mr. Prashant is interested. What about the others? So if you're interested, we can just like have a quick look at that. So shall we look have a look at the demo? So I had prepared a small MATLAB code for you to as a demo. Uh, so let me just share my screen. So if you have directly an access like to MATLAB to a MATLAB license, then that's good. So you can also try it on your own. If you don't have access to MATLAB, then you can also try the same or similar thing on Octave. So Octave is another similar a software which is like very similar to MATLAB. So the it has the like the syntax is similar to not if not exactly same, but it is similar to what you have for MATLAB. So then you can also like it's a free and open source equivalent of MATLAB, you can say. So you can also try it on that, like if you don't have access to a MATLAB license. Um, yeah. So the first code which I wanted to show you is for like basic damped vibrations. So viscous damp like vibrations with viscous damping. So here it's basically I wanted to show you about so like forced vibrations with viscous vibration, viscous damping. So in this code you can basically provide the time interval over which you want to the uh, in which or like the time interval over which you are interested in knowing the response. Then you can provide the basic mass, stiffness, and damping properties. So in SI units, and so here I'm calculating the critical damping, and from that you can basically calculate the damping ratio. So then so I'm considering a harmonic forcing in this code. So like let us say there is a sinusoidal forcing with a certain amplitude f naught, and W is basically the forcing frequency in hertz. No, it's basically in radian per second. Sorry, so it's in radian per second. So then, and then you can also provide the initial conditions like the initial displacement and initial velocity if you have if any. And since we have provided the stiffness and mass properties, so you can calculate the natural frequency and damping ratio and the frequency ratio. So those are the basic parameters that so we can calculate from the information, and then we can so this code part of the code, this section deals with the analytical solution. So we have basically a forced vibrations like a single degree of freedom system on which a forced vibration like is acting. So it's basically a simple spring mass damper system on which we are applying a sinusoidal or harmonic forcing. So then the response will have like two parts, which is basically the steady state part, or which is the particular integral, and then the transient response, which is basically the solution to the harmonic, sorry, to the solution without the harmonic forcing, or the homogeneous differential equation, or which is also known as the complementary function. So that is the transient response. So and then we can combine these things together to get the total response. So now the transient response for the case of viscous damping will depend on what the value of the damping ratio is. So if the damping ratio is greater than 1, then that will be over damped, and if it is exactly equal to 1, then it will be critically damped, and if it is less than 1, then that is under damped. So based on these three cases, so our response, like the function, complementary function, or basically the response, like basically the free vibration response will change, or the transient response in this case, because it's a forced vibrations problem. So that is basically addressed in this section. So if it is under damped, then the response will be something, and then we have the yeah. So depending on, now we have already the initial conditions, and so based on that we can find out the unknown constants for that, so for that particular nature of the response that is expected for, like, depending on whether it is under damped or over damped or critically damped. So we already know, we have like studied the particular expressions for each, for free vibrations in each case. So this part of the code contains basically the uh, expressions for that. So I will not go over the code like line by line, but broadly what I am just trying to explain you is that, so each part is basically, it's like an if else uh, thing, like, so where you have, depending on the value of the damping ratio, it will select the appropriate expression for the complementary function, and then determine the value of the unknown constants a and b or whatever in that case, and then find those, and then find out the total response, and then here we will plot the response for a certain whatever given damping ratio or whatever. And then you have, in the next section, you have the numerical solution for the differential equation using the ODE 45 solver. So up to this point, anyone has any doubts? Anyone has any doubts on whatever that I am sharing? Okay. So you can, I think these are like simple things, and you can actually write your own code for this thing. So yeah, so this second part is the numerical solution of the differential equation. So here you do not actually bother whether it is like under damped or over damped or whatever. So here you actually find out the response by using some of the inbuilt solvers for solving basically the differential equation over a given time interval. So ODE 45 is one of the solver which is based on the combination of the fourth and fifth order Runge-Kutta numerical method for solving a differential equation. So it basically tries to integrate the differential equation in a, you can say, adaptive. So it has an adaptive time step. So you provide a certain basically a minimum uh, or whatever time step, and so it basically, based on the gradients involved, it can basically select its appropriate time step for integration for the differential equation on its own. So the inputs to this solver are basically the differential equation in a state space form. So where you have so you break down this second order differential equation. So basically you provide it a function handle which will provide you the output in this way. So like basically the differential equation is for the simple whatever single degree of freedom like damped vibrations. So the differential equation is a second order ordinary differential equation, right? So this needs to be decomposed into a system of two first order differential equations. So that is being done here. So here the first equation so is basically that. So in this solver the two like the x vector, so x is a vector and y is also again a vector here. So x is a vector which contains basically two things. On in the first row it contains the displacement of the system, and x dot, it's a second row is x dot. So x, so it's a vector of x and x dot. So you use that. So the first equation that we write is that uh, x dot is basically the second row of this x vector, and the second equation is basically that x double dot is equal to this. So which is so you basically rearrange the differential equation for the problem in this way. So if you're not able to understand what I'm saying, so I think you can read the documentation for this solver ODE 45 for like more information. So it has a very good explanation of how to use this for different kinds of problems. So if you have like any uh, differential equation that you want to solve, so this is like you can give so you can try this as the first, the initial way, initial solver to try. You can consider like ODE 45 is a good choice to uh, solve any differential equation. Yeah, so this like basically the function over here, whisk damp force vibration, so it contains basically the decomposed second order differential equation. So it breaks it down into a system of two first order differential equations over here, and that provides you the vector x and x dot y, which is contained in y. So y is contains basically x dot and x double dot. So yeah, so it basically gives you the instantaneous gradient um, of the, you can say, in the state space form. And the other inputs that you need to provide to it is basically the time span, and then x naught is the vector which contains the initial conditions, basically the initial velocity and the initial uh, displacement, initial displacement and initial velocity x naught and v naught. And then so you basically the output of this solver is the time and the x vector. So the x vector or x matrix contains basically the displacement and velocity as a function of time, so that the output that you get is this. And then we can plot this. So the next section is basically where we plot this two ways of solving this differential equation. So we initially solved it analytically, depending on the physical properties of the damping ratio, stiffness, mass, and damping, and etc. And then derive the response from analytically, because it's a simple system which is a simple spring mass damper system. So you know the analytical solution over here, and then you are also solving it numerically using this ODE45 solver. So this example will illustrate that whether the numerical method is accurate or not. So yeah, here is a sample. So I just tried to run the code, and this is a sample output. So for the given mass, stiffness, and damping combination, the damping ratio comes out to be 2.5. So in this figure, so you have basically the response for the numerical as well as analytical method, and you can see that both of these curves are closely overlapping. So you can play with this code by varying the damping. So let us say it was 1000 earlier, so let us reduce it to 100. So then it will now become underdamped. So now, because this is a forced vibration case, so then after a certain time, the response will start following the forced vibration. So you can see that this response tries to mirror the. So in this case also you can see that initially there are some transients. So for the damping ratio 2.5 case, so up to let us say 1 second or so, you have some transients, and then onwards the response is basically just mirroring the uh, forced like so the it is oscillating at only the forcing frequency. So the effect of the uh, free vibrations is almost not visible after 1 second. So likewise, so you can try to change the damping ratio, mass, stiffness, etc., and then try to see that the how the response is for different cases. And so you can see from this figure that both the numerical and analytical response are in very good agreement. So so that shows. So in some cases you might encounter some cases where you do not know the analytical solution. So in that case, so the numerical solution is the only way to solve the differential equation. But uh, just a moment. So I just need to take a call. So sorry, yeah, sorry for the disturbance. Hello? Yeah, sorry for the interruption. So I actually had to take an urgent call. Yeah, so basically I was discussing regarding this MATLAB code. So anyone has any questions related to what I just discussed? Yeah. So if you want, I can share this code with you and you can try it out on your own. Is it possible to combine these codes in two .m files into one file? Yeah, so the thing is that uh, you need to write. So why there are two M files is this because one of them is basically for the function and other is basically the main MATLAB code. So that's why you have to. So if you have a way to define the function like in like in the same MATLAB file here, like here in the main MATLAB file itself, then you can do that. Otherwise, you can create a separate MATLAB code for the. So what I'm basically talking about is that so you have the main MATLAB file here, which is damped vibrations.m, and the other one is basically the function here, which we are writing. So that's why you have these two .m files here. Yes, I will solve assignment questions. So this was just a demo for you to kind of get an idea of how you can use like these tools like MATLAB. It's not part of the course as such. This is just like an extra thing that I prepared like on my own. So I had another demo which I had prepared, but if you want, like I can like skip that for now and like we can maybe solve the assignment type questions first, and then later on if time is left we can go through that other MATLAB code demo. Is that okay or okay? Fine. So then we can start with some of the sample assignment type questions. So I had picked up some sample problems which are similar to the assignment ones. So I had picked up some sample problems. So if you do you have any specific uh, problems that you wanted to like discuss or like so then you can also tell me those. we can discuss those problems in the session, or else we can just start with the sample problems that we have. So shall we start with these problems that I had picked up? Yeah, okay. So yeah, so the first problem is this one. Which of the following instruments measure the amplitude of a vibrating body? So which one do you think uh, measure the amplitude of a vibrating body? Both A and B. Right. So the answer is correct. Both A and B, vibrometers and seismometers. So you might have heard about the instrument called stroboscope. So so which one is true about stroboscope? So what do you think the is true about the stroboscope? A, okay, option A. Yes, so that is correct. So stroboscope is an on-contact type frequency measurement instrument. So so how many of you have actually used a stroboscope? How many of you have tried somewhere in your institute or whatever? Has anyone tried out? Okay, so I think if you have like access to a stroboscope, so I think you should definitely try it out. It's a very interesting, way to measure frequency. So, so like if you have a certain, so let us say if you have a rotating wheel and you basically try to vary the frequency of the stroboscope so that that whatever oscillating body or whatever that appears almost stationary like so it's a very interesting experiment to do. So and I think if you have access to it, I think you should definitely give it a try. So yeah, so a device that transforms values of physical variables into equivalent electrical signals is called. So we just discussed that at the beginning of the session. So what is that? Yeah, so it's basically a transducer, right? So anyone knows what is a tachometer?
Yes, a tachometer is used to measure the speed, rotating speed.
Sorry, can you share again?
Sir, it is used to know the RPM of any
Right,
machine.
right. It's used for RPM measurement generally. Right. So you basically I think uh, match the tachometer with the wheel axis and then it gives you the RPM. Yeah. So in this problem, like for proper vibration isolation in a forced excitation system, so how should we select the spring here in this case? So So for this, let us look at the basically for the simple spring mass damper, like the so let us look at the basically the frequency response curve. So for a vibration measurement instrument, so this is basically the plot of so it's basically a plot of this thing, this whole thing. Uh, so let us say this is with respect to r, and this is like z by y mod of that. So where z is the relative displacement between the body and uh, the basically the excitation. So let us say the surface of uh, surface is being excited. So this mass is being is oscillating at, let us say, x. So z is basically x minus y, or basically the relative displacement here between the motion of the base and the uh, mass involved in the vibration measuring instrument. So in case of a proper for a proper vibration isolation case, which part of the curve do you think we should be looking at? Trailing part, right? Yes. So you are right. So it's basically, yeah. So it's basically greater than r equal to 3. So why do you think it is greater than r equal to 3? Yeah. So you have to have like basically low transmissibility. So then the relative displacement will and the actual excitation will be nearly comparable, and so there will be less error in the measurement. So with the proper isolation, so for that we need to have r is greater than or equal to 3, so that the transmissibility is low, and the difference between z and y should be, yeah, so to have z is nearly equal to y. So in that, so when we have r greater than or equal to 3, so in this part, so you have this basically is z by y is equal to 1. So this horizontal line which I have drawn, so I mean basically this line, this horizontal line, so it's basically representing um, z by y is equal to 1. So when r is greater than or equal to 3, then this will be nearly asymptotically converging to z by y equal to 1. So then, so there will be lesser error in the measurement. So with that, makes sense. Shall we move to the next problem? Yeah, so in this question, so here like there is some small problem in displaying the options. So sorry about that. So I'll try to correct that in the slides that I share. But basically, this question is about a vibrometer, and it says that it shows 5% error in measurement, and its natural frequency is 4 hertz. And if the lowest frequency that can be measured is 8 hertz, so then what will be the value of the damping ratio? So how do you think we can solve this problem? So I'll give you a minute to think about how do we solve this problem. So anyone has any idea how we can solve this problem? Yeah, right. So it's basically same as using the relation of Z by Y. So it's because it's a vibrometer. So Z is the measured quantity and Y is the input. So then what it's actually, so then error of 5% means that, so Z minus Y by Y is basically 5 by 100, right? Which means that Z by Y is equal to 1.05. So Z by Y is 1.05, and then so you can use the same relation that uh, we had like just discussed that, so since the natural frequency is 4, so basically R will be basically 8 by 4, or omega by omega n, so which is equal to 2, right? Because we are measuring up like the, yeah, so because we are why we are adding point 0.05 rather than subtracting, is because if you look at the curve that we just discussed, um, so you can see that Z by Y is always greater than 1 for the part of the curve where in which we are basically looking at. So here R is equal to 2, or basically R is greater than 1 in this case. So then Z by Y is always greater than 1 in this case. So the error in the measurement, which is basically the so which will always be greater than 1, so the error will be positive always in this case. So does that answer your question, Mr. Amit? Yeah, right. So right, so thanks for bringing that up actually. Yeah, why should it be plus 0.5% and not minus 5%? So right. Yeah, so that's why, so then we are Z by Y is 1.05, and we know R is equal to 2, and so Z by Y is equal to the our usual familiar relation of this. So from this you can substitute the required quantities. So what we will get is, so since R is equal to 2, so the numerator will be basically 4, R square is 4 by root of 1 minus R square, which is 1 minus 4, plus 2 zeta R, 2 into R, which is basically, so 2R is 4, so 4 zeta whole square is equal to 1.0, sorry, oh sorry, So you can rearrange and then again, so you can square both sides, and then you will basically get that 4 by 1.05 whole square minus 9, which is 3 square. Uh, so that is 16 zeta square. So I got the answer as 0.587 or something. So 5 uh, so what about the others? What did others get? Yeah, so yeah, 0.5869, right, exactly. So I also got the same answer. Right. So did everyone get uh, how we solve the problem? So if yes, so then let's move to the next problem. A vibration measuring device is used to find the acceleration of a machine running at 200 RPM. So if the natural frequency of the instrument is 10 Hertz and it shows a displacement of 0.008 centimeters, so what would be the acceleration reading? So I'll again give you another 1 minute to think about how we solve this. So anyone has any idea how to solve this problem? Anyone has any idea? Right, exactly. So using the relation z by y. So yeah, so z is the thing that z is not given actually. Z is the thing that we need to find out, or basically or in other words, the acceleration reading. So z is something that we are actually measuring, let us say, in terms of acceleration, uh, and y is the actual displacement, or let's not call z. So it's basically the acceleration reading. So acceleration, or let's yeah. So first let us write down our basic relation for z by y. So z is the measured like relative displacement, or actually the reading as such. So accelerometer gives us the quantity which is proportional to the acceleration, right? So uh, our usual z by y relation is whatever this. So here we know that the machine is running at 200 rpm. So whatever, let us say there are some excitations because of the some unbalanced mass or whatever. So then that will be at the frequency of basically the machine. So the machine is running at 200 rpm. So we know what is the frequency of that. So we can convert 200 rpm into radians per second, or if you want to like have it in hertz. So it's basically 200 revolutions or 200 cycles in 1 minute, or so it's basically 200 by 60 hertz. So which is 10 by 3 hertz, let us say. And there is no mention of any damping as such, explicitly. So then we have no option other than assuming some value of damping. So let us assume it to be 0 for simplicity. Right. So R, so yeah, so it's basically R is the frequency ratio, which is omega by omega n. So omega n is 10 hertz, and the actual omega is 10 by 3. So it's basically 10 upon 10 by 3 by 10, or 1 by 3 basically. So R is basically just 1 by 3. So R is known, and let us say zeta is 0. So then this term becomes 0. So it's basically just z by y is r square upon 1 minus r square. So the acceleration reading as such will be in terms of uh, so then the acceleration reading we can write it as r square y upon 1 minus r square. So the displacement is given as 0.008 centimeter. Okay, so z by y is 0.1247. Okay. Yeah, and it is given that y is 0.008 centimeters because that's the actual displacement, uh, let us say. So then that is r square. Yeah, so I got I like z by y as 0.125, and so it's basically 0.125 into, so the relative displacement comes out to be something about 0.001 or something, and then the acceleration reading will be basically just omega square z, right? Yes, so someone raised their hand. Yes, so can you just unmute and speak?
Sir, this question says the natural frequency of device is 10 hertz
Right.
and it shows a displacement of 0.008 centimeter. So I think this is the relative displacement of the device, but you have taken it as a y. It should be z, sir.
Okay, okay, sorry. So it's actually Z, so right, right. So the displacement is actually 0.008, so yeah, okay, Z is 0.008. Yeah, so then Y, so you can find out Y, and then that acceleration you can, yeah, sorry, I actually missed that. Right, so Y is actually is something that we need to find out. So yeah, sorry for that confusion. So you're right. So y is actually 0.008. It's already given, and so the z you can find out. So z actually will then come out to be 0.001, right? No, sorry, I'm sorry. Y. So yeah, sorry. Z is given as 0.008, and we need to find y, right? So then it comes out to be 0.064, and then omega square y will be, so it comes out to be something like 28.07 something. Is that the answer that you got? Yeah, so right, right. So yes, yeah, right. So yes, so it will be omega square y will be 28 something. So the answer is option A in this case. All right. So let's move on to the next problem. Yeah, so yes, so Amit, sir, you wanted to ask something?
Sir, can't we solve this question like that? I have tried in a. Sir, we know z is equal to small z sine omega t minus phi.
Okay,
If we differentiate two times, we can get the direct equation for z double dot.
right.
And the modulus of this equation will directly give you z double dot. Why we are calculating y here, sir?
No, it's basically so Z is a quantity that is being given, but there is like the error in measurement comes comes because of the difference in the frequencies, right? So the natural frequency, so the behavior, basically the frequency response curve that we like discussed earlier. So Z by Y will actually depend on the frequency ratio, right? So so what is the actual acceleration reading that we need to find out, so that we are calculating using y, right? So y is the actual base like excitation or actual, so the actual acceleration is omega square y, and we are measuring z, and then we have to basically, so the z by y thing depends on the frequency ratio, so that's why we are calculating z by y. So how are you going to calculate? So if you write, let us say, whatever z is equal to something sine omega t or whatever, and yeah, so the magnitude of that z thing will be 0.008, right? So then z double dot will be the uh,
Minus omega squared z sine omega t minus phi.
right, right,
So
exactly.
if
So
if we find the modulus of this equation, sir, can't we get direct value of z double dot, sir?
you can get z double dot, but the actual acceleration of the body is actually omega square y, right? Not omega square z. Z is the relative displacement, right? So
Sir, but we have to calculate the relative acceleration because the instrument has been mounted on the machine, so we have to calculate z double dot, sir.
okay, but the actual acceleration of the body is something that we need to find. So that's why like we are, yeah. So the reading
We
and the
have to
actual
calculate the reading in the instrument, sir.
so then that will be actually right. So yeah, so that will actually be omega square z, right? You're right.
So, sir, why we? I think we should not go for y here, sir. Am I right, sir?
Yeah, so omega square y will be the actual acceleration, and what we are measuring will be probably, yeah, so you're right, so it will be actually omega square z in that case.
But sir, answer is not matching, sir.
No, so
Yes, sir. I also can't able to get the answer.
sorry, can you say again?
Sir, while calculating omega square y, I can't able to get 8.07. What we have taken the value of omega, sir.
Omega is basically the what we got as this 10 by 3 hertz, this one.
So, sir, when I am squaring 10 by 3 and multiplying 0.064 into it, I can't able to get 28.07.
You are not able to get 28.07. So it's 0.064. So it's basically in hertz, right? So you need to convert it into radians per second. So omega is 2 pi into frequency in hertz. So it's not
Oh,
like
okay, sir.
3.33 hertz, like, but that into 2 pi. So that's how you can get 28. So what I actually skipped one step. So basically, so omega square. So I calculated omega square y. So I think you can either read. So you, if you want to calculate the acceleration reading, right? So you are right. So we need to calculate omega square z. But if you want to calculate, let us say the what is the actual acceleration, so then we need to calculate omega square y.
Okay, sir.
Yeah. So omega square y will be 2 pi into 10 by 3. So yeah, thanks, Amit sir, for pointing that out. We need to calculate z for what? So the question, yeah, so z is basically the relative displacement or what is actually being measured by the instrument. So if you did not understand what I meant by z, so let us say if this is some, so there is some, so let us say this is the box, what is contained inside the box is, let us say, the accelerometer, and I am mounting it on top of this, uh, let us say this is the machine here. So this is machine is, let us say, moving at as per, let us say, y, some y displacement, and the mass inside this is, let us say, moving as per x. So the relative displacement will be x minus y, so that is basically z. So that is actually being measured by the vibrometer, or in case of accelerometer, it's basically measuring it as a proportional to acceleration, so it will be basically omega square z that's actually being measured.
Sir, if we take omega square z, we will get 3.5 centimeter per second square, sir. But there is no option available in the four choices, sir.
Yeah, the option that may be wrong. So So we need
Yes,
to,
sir. Actually, it is asking omega square y only, sir. The question has been framed using omega square y only, sir.
right, exactly. So you can say it should be rephrased basically into what is the actual acceleration of the machine, and what is being measured will be basically omega square z, as you said. So that comes out to be uh, something like 3.5, right? Now here, because r is 1 by 3, we are actually in some other zone, like we are, if we look at the frequency response curve, so we are somewhere operating here or somewhere, like r is less than 1. So I just made a mark on this, so the blue mark here, let us say here, so we are operating somewhere here. So if the frequency ratio is kind of somewhat high enough, then the error in the measurement will be very significant. uh, so so shall we move to the next question? Basically, we are interested in finding the vibration of the structure y or y omega square by measuring z. Yes, yes, you're right. Yes. Yeah, sure. So let's move to the next problem. Yeah, so I think one interesting thing, I don't know whether you have discussed that in the lectures or not, but for the vibration measurement instruments, essentially the z by y as such relation is basically will remain the same. By changing the vibration measurement instrument, we are basically just operating in different zones of this curve. So anyone can just point out which zones are we operating for which instrument?
Sir, for vibrometer and velometer, we should prefer to operate R greater than 3, sir.
Right, exactly. So
And for
there,
acceleration, we prefer R to be very small, sir.
yeah, exactly. So for that we need, yeah, so vibrometer R greater than 3 and R less than 0.5. Okay, right, exactly. So
Sir,
that's why, like,
this
in,
this
yes.
this question which we have just completed, sir, this is a vibrometer or accelerometer, sir?
Sorry, can you just, I didn't get your question. Sorry.
Sir, this question we have just concluded.
Yes.
This
Yeah.
talks about which type of instrument. Is it a vibrometer or accelerometer, sir?
So accelerometer.
Because sir, it is like it is measuring a displacement of 0.008 centimeter, and again it is saying acceleration reading.
Yeah. So the thing is that, so you can interpret it as a displacement or acceleration reading depending on like, so you can based on the like, let us say, measured displacement, you can calculate it like in terms of like acceleration also. So whether you call it a vibrometer or an accelerometer as such, like there is like it's just a difference of the name. Essentially the model of that system is like the same. It's the same thing, like it's basically just same as that. You have this spring mass, suspended spring mass damper or whatever system, and so this is the vibration measuring instrument, and you attach it to the like base of the machine. So the like the black one is the machine, so that is moving at y, and this is moving at x. So now if we can measure x minus y, so that we generally call it as vibrometer or seismometer or whatever. And if we are measuring omega square z, like a signal which is proportional to omega square z, that we call it generally as accelerometer, because it is proportional to the acceleration, right? So I think you need not get confused by the nomenclature. If some, like the measurement was, let us say, given so let us say the relative displacement was like measured to be 0.008. Now if we want to measure it as a signal proportional to the acceleration, then what would that reading be, if at all, like if we are measuring it using like this same principle as a signal proportional to the acceleration? So then that would be that thing. So yeah. Okay. So now let us move on to the next question. So here in this question we have an accelerometer which has, so the suspended mass of the accelerometer is given as 0.01 kg, and the engine is undergoing an acceleration of 9.81 meter per second square, and the engine is operating at a speed of 5000 rpm, and the recorded acceleration is 10 meter per second square. So now here we are like clearly given that the recorded acceleration, let us say, is 10 meter per second square, but it's actually undergoing an acceleration of 9.81, right? So what is being, let us say, omega square z is 10 meter per second square, and omega square y is 9.81 meters per second square. And we have been given the operating speed of the engine as 5000 rpm. So omega will be basically 5000 into 2 pi by 60. So in terms of radians per second, it is comes out to be 523.6 something. Now it is given that the damping ratio is 0. So then we use the same relation that we used earlier, that z by y is r square upon 1 minus r square, right? Now since we already know omega square z and omega square y, so the ratio of that will be basically z by y. So it is basically same as 10 by 9.81, right? So r square upon 1 minus r square. So 1 minus r square is 0.981 r square. So r square is basically 1 upon 1.981. Or in other words, basically r is square root of so I got r is something as 0.71. So did anyone try to calculate? Yeah, so I got 0.71, so you also got same. Yeah. So r is basically omega by omega n, and omega n is root k by m. So from that we can basically find out the stiffness. So 0.71 is omega by omega n. So omega is already known, 523.6. So omega n will be so the stiffness will be so omega n square into the mass, which is 0.01 kg. So in kilonewtons per meter, so it comes out to be something like 5.43 kilonewton per meter. Yeah. So is this correct, or anyone got any other answer?
Sir, I am getting the same answer, but the same question has been given in the assignment also, but none of the option gives you 5.43 as the answer, sir.
Oh,
Sir, no
yeah, you're
option is
right. So there
available.
is, yeah, so the option, yeah, so it does not match with the options, right? So yeah, I took this question from some reference, and I didn't realize that. So so let me check this question, and yeah, 180.2. So I didn't realize this question was also in the assignment. So sorry, I actually missed that. So is this in the same assignment for the week 5 also? Like, is this, so are
Yes,
there
sir.
any questions that are repeated, apart from this, like, are there any questions that are repeated in the assignment? Like,
Yes, sir. Almost same questions are there, sir.
oh, is that so?
Yes, sir.
Oh, I didn't check that actually. Sorry. I didn't realize that. So, okay. So it's like, are the, like, all the questions say appearing in the assignment for this week, like, which I have solved?
Yes, sir. Same question, sir.
Even the values are same?
Yes, sir. Exactly same. Even same option, sir.
Oh, okay. I didn't realize that actually. Yeah, okay. Okay. Anyway, yeah, sorry. Yeah. Anyway, so let me check with that question, and I'll get back to you. So on Friday, we are again like meeting for the next online session. So I'll just clarify on that.
Sir, because tomorrow is the due date for submission, sir.
Oh, I see. Okay.
Sir, for this question, we can use this relation, sir. I have mentioned in comment box that measured
Okay.
acceleration divided true acceleration.
Okay.
So when you take r square towards left, so that will become z omega n square divided by y omega square. So the remaining
Right.
term at the right hand side, that will mean only 1 divided by 1 minus r square. So using that relation, we can find r, and then we can find k.
Oh,
R will
okay.
be in 0.137.
So do you get the like option as
Yes,
like
yes.
one of the answers as one of the options?
What are the options? 146. I think previous is the question. Question. Yes, yes. Option is there, sir. 146 is the answer.
Okay, you get 146 as the answer.
144.29 approximately equal to 146.
I see. Okay. Okay.
It's using this relation mentioned in this.
Right. Right. Yeah. I'm just looking at that. Measured acceleration by true acceleration. Okay.
It's
So
taking towards left, so that will become acceleration.
okay.
Which that will not remain towards right in our right hand side.
Right. 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 Okay. Okay.
In that way, that will answer. That answer will correct.
Okay. I see. Okay. Okay, fine. So uh, let me check again, and yeah, I'll just let you know. So yeah, I think, yeah, I'll check, and then let's proceed to the next problem. So is this problem also there in the assignment which I'm now sharing? Can someone just check that?
Sir, with different values, sir.
Okay. Okay.
Frequency ratio is 3 instead of 2.
I see. Okay, okay. Okay, anyway, so we can just go through that. Uh, so again, it's like the same thing, Z by Y thing, and so you have been given zeta as 0.8, and R is 2. So just need to. So you just basically need to, in this question, we just need to substitute the values of R and zeta, and then you will just get the answer. So, so I think I got 0.91, I think. Right, so yeah, so I think the answer is 0.91. Yeah, so if the problem that I'm sharing is like exactly same in the assignment, so just let me know. Uh, I will not go through that. Oh, okay. For the assignment, it is not matching with the options. Okay, I see. Yeah, I think then you can report these things like in the whatever that in the discussion forum. So I think they will not consider that question for evaluation in that case. Okay. So now is this question again same as the question in the assignment for this week? I see.
Yes, sir. The same question is there, sir.
Oh, I see. Okay, okay. So somehow the questions like we are referring to the same set of questions or our reference seems to be the same. Anyway, uh, so then I will not go through the question because I'm not supposed to solve the same question as that in the assignment. So I think even this question is there in the assignment. So
Sir, the question is same, but I have a doubt in this question, sir.
okay, what was
Sir, can you show the same question again, sir?
yeah, this one, right?
Yes, sir. Yes, sir. Sir, what is mean by here the total displacement of the mass? Is it talking about Z or X, sir?
Total displacement of the mass of the pickup, that is x.
Because, sir, it is saying it is observed. So generally, Z is observed by an instrument, sir.
See, that absolute displacement of the mass of the pickup inside the thing is x, right?
Okay, sir. So should we should take it as a X, sir?
Yeah, so where is it saying observed? Ah, okay, is observed to be okay, something. No, the absolute displacement you can say that it is observed to be 10 mm, but it's not like something that you can directly measure. So,
Okay, sir.
like that, yeah.
Okay.
I think this question is not there in the assignment, I think, right?
Yes, sir. No, not there, sir.
This is not there, I think. Yeah, so I think then we can go through this question now. Uh, yeah. Oh, I think I missed the figure. But yeah, from the question we can make out what is there. So basically, yeah, I can draw the figure for you. So this is the mass suspended in a box by a spring. So let us say this is this mass, and it is put on a platform, so which is having a oscillation vibration of like y sine 8t in centimeters. So it is asking that, so the question is asking that what will be the relative amplitude. Yeah, so what you are given is that y is sin 8t. So which means basically capital Y or the steady state amplitude is 1, right? And omega is 8, right? And we also know omega n, which is root k by m.
Sir, it comes out to be 40.
Right. So then R will be 1 by 5, right? Omega by omega n. So there is no damping here. Let us assume that there is no damping. So it will be r square upon 1 minus r square is equal to z by y. So I got the answer as 0.04167. Yeah. So I got basically Z is 0.04167. So which matches with the option C. So did everyone get the same answer? Okay, sure. So yeah, so that's the last question I had in this sheet. Then I had, yeah, so does this, I think this question does not appear in the assignment, right? I think for this week. So maybe we can go through that. Yeah, so it's not there in the assignment. So let's go through that. So yeah, so if the difference between the maximum and minimum recorded values is 8 mm, find the amplitude of motion of the vibrating structure when its frequency is 50 radians per second. Okay. So we are given that natural frequency omega n is 4. Zeta is obviously given as 0.1, and difference between the maximum and minimum recorded values. So what does that mean? Yeah, it's actually 2z, right? Because it's basically the peak to peak amplitude, right? So yeah, so it's the range, so it's like 2z, right? So it's basically 2z, which is 8 mm. So basically z is 4 mm. So for omega is equal to 50, so we have r is equal to 50 by 4 omega by omega n, which is 12.5. Now for this r value and zeta being given, zeta is 0.1. So we can calculate z by y. So we know z here, we know r, we know zeta and everything. So we need to find out y. So yeah, so I got 1.0063 as the answer for z by y. So did everyone get the same answer? And I got the value of y as 3.975. But that is not matching with the options actually. So, but yeah, so anyway, but basically the method as such I think is the same thing. Like, I don't know why it does not match with the options, but because it is asking the actual amplitude of the vibrating structure, so which is actually y, and what we are measuring is z, so that is already given. So y is equal to 3.975 should be the answer. So I think, yeah, so I think it's almost time up for this session. So any other questions or comments?
Sir, can you show one of the earlier question in which it was asked what is the condition to satisfy if we want to have proper vibration isolation, sir? There was the objective question, sir.
Okay. Uh, okay. So was this question also there in the assignment?
Sir, not exactly. Actually, my viewpoint is that answer should be greater than root 2, sir. But you said it should be greater than 3, sir.
Greater, like it's like uh, see the for r is equal greater than 3 or something, like then the z by y value is like
So
closer to
that is a
1.
condition for design criteria of the vibrometer, sir. Greater than 3, sir.
Yeah.
But in this question, it is asked for proper isolation to be effective, sir.
Yeah, so if you want, like, yeah, so you're right. So in your case, like, if you are, we are just looking at for vibration isolation. So in terms of only transmissibility, like
Yes, sir.
for greater than root 2, then transmissibility will be like less than 1. So yeah, so you are correct in that sense. Yes, you are right.
But
Definitely.
sir, there is no option available in the four answers given here, sir. Greater than root 2, sir.
Yeah, so forget about the options in this question. So it may not be, accurate or in that sense. But basically, if you
Yes, sir.
want to, I mean, uh, put it in terms of like only vibration isolation in terms of from a transmissibility point of view, you are right that it should be greater than root 2. That is sufficient. But like let us say if we want to say that for a vibrometer or something where so Z by Y should be comparable, so the error should be small, so then R is greater than 3 is better.
Yes, sir.
Yeah, so I think, yeah, so you're right in terms of only if we are looking at only in terms of transmissibility point of view. Any other questions or comments? If not, then I think we can close the session for today. Thanks a lot for joining. So I also have another demo for you. So maybe I think in the I'll show that demo in the next session. So if you want, so you can like if you want the MATLAB code, so you can just write an email to me on. So I'll just share my email address. Or if you have any questions, so you can reach out to me on this email address. I have shared my email address in the chat. So if you want the MATLAB code or something, if you are interested, so you can write an email to me, or if you have any other questions also, so you can reach out to me on this email. So that's all that I had from my side for today's session. So thanks a lot for joining. So let's meet on Friday for the next session. Yeah. Thanks. Thanks all for joining. Good night.